So the meetup group is a data science meetup group, and when I was planning this talk, I was really afraid that um, working in security, I don't really have much data science material to talk about. I know there's also some people from security here, and focusing the talk on like the tools that I would do, that also didn't really appeal to me. Um, so what I decided was that you guys probably know more about machine learning algorithms than I do. I don't have any particular expertise in that, and a lot of you probably know more about security than I do. Instead, what I can offer you is a method for making both of those things more efficient together. And that's what this talk will be about. So my name is Michael Roytman, and I'm the data scientist at Risk.io. Risk.io is a platform that predicts where security intrusions will happen. So we automate security analysis and we automate security vulnerability management. So when I came to Risk.io, we were just starting to build out our predictive analytics functionality, and I've been wrangling that process ever since. When I started, we didn't really have Hadoop clusters. We didn't have Hive or Spark. We didn't have any custom machines running in our own data center. And I don't even think I knew what machine learning really was. I just knew about some algorithms. I'm really proud to say that my data science operation has kept everything that way, except that we got rid of MongoDB. You might say, such wow, so few science, but you'd be wrong. In fact, this is very intentional. And by intentionally limiting our complexity, both statistical and operational, we can generate actionable insights and do that cheaply. So let's start with how we do that. Less is more is the first part of the talk. And while I don't like dealing in platitudes, taken on face, this is a pretty meaningless statement. But today I want you to consider situations and impacts that resist the current trend of more data science, and more Hadoop. Yes, it's 2014. Yes, this is a data science meetup. But that doesn't mean that old methods for generating value from our data don't work. We don't need to buy tulips to get a lot of the insights that we're getting through some of the more complex operations. So there are four contentions to my rant about data science. The first one is that there's a propensity to implement really complex tools and to maintain them without any real explicit need for them. I think trying to analyze whether that need actually exists is pretty important. And I'm versed in Hadoop lore. We thought about implementing Hadoop at Risk.io. But there's only a slight difference between forcing a need and overspending. And there's some really good examples of people doing that. Second, data is everywhere, and so are data scientists. It's surprising and wonderful how much data-driven work actually happens in other aspects of the business that can bubble up to a data science practice. It's just that the directive needs to be one that is more explicit about what we call data science. Third, collecting all the things is awesome, and I know there's some good Google papers about how there's an unreasonable effectiveness of data is a pretty popular one that talks about how, just getting more facets and running algorithms on the thing will tell you a lot about a tool. But that data comes at a cost. There's a cost of storage, there's a cost of cleaning, and there's a cost of complexity. It's important to know which questions you're answering first and before you begin. And lastly, all of these constraints are actually blessings. Much like our beloved Twitter, limiting the scope of something to 140 characters makes for a much more precise and useful product. So I'll talk to you about these contentions, but afterwards I want to talk to you about what we do at Risk.io specifically, which I think is a manifestation of this kind of data science operations philosophy. Hopefully more impact. So as resistant as people are to change, I hear a lot of organizations jumping the gun on technological organizational change. I want to explain an ongoing trend I like to call knee-jerk Hadoop. So tons of organizations, when they implement business analytics, think they'll get a fast data store or a mature analytics practice just because they hired 5 people who have some experience in Hadoop. A horse and a horn, though, does not make a unicorn. Real efficiency comes from understanding the runtime complexity of your algorithms, of your backend, and of making that as efficient as possible. That takes time and specific knowledge of the system, and I don't think that's dependent on which tools you use to analyze it. Sure, like afterwards, Hadoop might be super useful, but if you don't understand where the complexity is happening and what the runtime is, you're never going to get the benefits of something that fast. Next point is that you don't need to save for tomorrow what you could do in Excel today. This is probably a manifestation of the fact that I work for a startup, and we try to do things as agile or as quickly as possible, but in practice it's also true. Don't actually use Excel, use R or something. Wizard is a really good tool that I've recently started using that's for the Mac, and it'll do regressions on the fly as you pipe data samples in, and you can then choose any permutations to build models pretty quickly. But what I'm trying to say is that data science work is often related to domain expertise, and I have the least domain expertise of security of anybody in my company, really. but I can talk to our marketing manager, get the right set of questions, and she can do 80% of the work in Google Analytics or Kissmetrics. There's no need for me to create new backend systems that will analyze the data about our incoming traffic. I mean, our CEO knows how to write a SQL query as well. If there are questions that are specific to him or specific to his domain expertise, there's no reason to offset that work to a different business unit when the one that's actually doing it could be answering those questions for you. So I'm the only data scientist at Risk.io. But our data science operation is probably close to 3 people. It's 100% of my time. It's a fourth of our CEO's time, a fourth of our CTO's time, probably another 30% of marketing's time, and 10 to 20% of a security architect. And what I'm trying to say by all of this is that the operation is both broader than you think, and you need less resources than you think by using both the domain knowledge and the existing skill set of people in your company. So at Risk.io, we launched our first predictive models in March of 2013, and they were just god-awful, crude predictions of the priority of vulnerabilities. So the concept was really interesting because you could make decisions about which vulnerabilities mattered, but, I mean, I wrote them. I don't have a background in development whatsoever. They ran on a Ruby backend. Some of them took half a day to compute. Some of them took multiple days to compute. They would pull stuff out of Mongo and then use that to look up MySQL aggregations, do some Ruby calculations, push it back up to Mongo. Stop me if I'm boring you with the technicalities of the thing. But I'm just trying to illustrate how awful and complex this thing was. But it worked. 1 year later, it runs every half hour, and indexing takes a few minutes. And we've expanded the scope of our model, which includes 4 times as many inputs. Our code is just smarter. Our algorithms ignore duplication at every step. We've scrapped Mongo. We've modified the query DSL for Ruby to fit our exact needs. We could have easily said, this is slow. Ruby sucks. Bring me some Hadoop, and let's fire up some clusters. Let's do this in Python. And that's fine. That probably would have worked, but it's a lot more expensive than you think it is, and it probably gets you there a lot slower than what we did. Besides, in the process, you learn a lot less about your actual problem that you're trying to solve. So here's what we gained operationally by not doing that. First is we saved the infrastructure costs. Second is we took the time to understand exactly what our algorithms need to do and what they are doing. We also found problems in our data sets that we then could fix. We didn't spend time or energy hiring or tasking our engineers with knowledge transfer. And we gained a clean and easy to expand analytics module, which requires no specialized skills to work with. We built this in-house as we were trying to analyze what was happening. So if my plane crashes tomorrow into the side of our product manager's house, a 20-year-old without any prior computer science knowledge would do just fine. And most importantly, we can still make that move when we need to. So because these tools are so nascent, now we have Spark and Julia. Last year, that probably wasn't even something on our radar. And these new tools have evolved. They might be serving our purposes better. So that delay also comes at an increased benefit of the new stuff. And so the last kind of takeaway about operations is that not all data is good data. So often there's a push for more data. The New York Times and Business Week articles you read that are kind of like, I think this is a philosophy of data science that maybe some of you already think is outdated, but it's collect a slew of data, unleash a kid from Brooklyn on it, and you can solve any kind of crime or problem you want to. I disagree. It's much leaner, and I mean leaner in the Six Sigma Deming sense of the word, to cut out the useless movements, to ask first the right questions, then collect the right data, and then generate the right answer. So there's a lot of uncertainty in what is correct data, and you might miss some things. But that doesn't mean that the answer to that problem is to collect everything. So here's how that works at Risk.io. We attempt to solve the contextual problem of which vulnerabilities put an enterprise most at risk. We have access through our partner channels and through open source data to every kind of security data under the sun if we wanted to. We could also just buy more data. But when deciding which data partnerships to pursue and what to do, we only care about a strict set of criteria that filters out the noise for us before we even talk to these people. So here's an example of one data source integration that I did last year. We had a partner that gave us really good data about breaches that are happening across something like 30,000 businesses. And the data would come in weekly buckets, and these buckets would shift by about an hour. So you would have counts for a week, and then counts for a week that was shifted by an hour, and that's really hard to get anything out of, right? So we talked to them, we tried to get them to do it. It was required engineering time on their part. So just to be able to get the granularity out of that data I had a 168 by 167 matrix that would on the fly compute every hourly, reduce the matrix and compute every hourly permutation to figure out where each one was. That's not an easy thing to write in Ruby. There's no standard method to do that, and that's the only way that data becomes useful in real time for us. To buy that kind of data set and then wonder whether it's going to be useful or not is pretty silly. There's a time investment and a cost to both thinking about the data and maybe to even using it that isn't factored into just thinking about acquiring it. So the last part is less model complexity. I hope I've driven home some points from operational lessons that I've learned about less data scientists, less data science tools potentially being beneficial. But now I want to drive home about model complexity. And this will show you, I guess, the lack of complexity in what we do, but also how intentional that is. So let's talk about actual information security. I think a lot of you might have come here to learn about that. The game of information security is largely that people have been ignoring security for a while now. It's only come to our radars in the past couple of years. Some organizations have been doing it for longer. But there's a lot of security debt in the same way that there's a lot of technical debt at a development organization. So a typical organization might have 1 million, 500,000 different intrusion points or vulnerabilities, and 10 engineers working on them, or maybe the dev team splitting some of their time and fixing them. And the question becomes, which ones, or which 10 or which 100 of those vulnerabilities per week are the ones that you should address and should spend your efforts fixing? Because if you're looking at the wrong ones, you're just going to get intrusions and breaches while you're also expending effort fruitlessly. So there's 3 things you can do about a particular vulnerability. You can accept the risk, and that means there is some risk it will get breached. Maybe it's behind a firewall, maybe it's too complex to exploit. You can repair the vulnerability, or you can remove the threat. And removing the threat is usually putting in some kind of control, like a firewall or isolating the machine. The rest of this talk is going to be about the strategies for doing that. And there's some pretty standard dogmatic ways of doing it that I'll talk about. Namely, it's called the CVSS score. But these strategies that are based on the score, they rely on true but often really irrelevant facts. And this construction, so I'm going to rip into a government standard that's pretty widely accepted and people might disagree, but the construction of this standard is something I dug into pretty deeply, and it's an example of all the things I talked about with data science that are incorrect. It used too many tools, it used too much data, it got too many people involved, and the model, while it might have a good fit, doesn't actually do anything. And I'll show you why it doesn't actually do anything with real data as well. So in part 1, I'll show you why and how I know that remediation strategy is wrong. And in part 2, I'll come up with a better way. And I'll do that in a hopefully data science-y enough way for all of us. All right, so the preamble's over. This is actual meat of the talk. The Common Vulnerability Scoring System comes out of the NIST, Institute for Standards and Technology. There's another organization called MITRE, which collects all the security vulnerabilities that exist or that get reported to it. So this is not all the vulnerabilities that exist in the world, but currently they're at about 64,000 different vulnerabilities across over 100,000 different products or product versions and types. And those vulnerabilities are types. They're definitional level things. So a Windows XP SP1 package that hasn't been upgraded has some kind of intrusion holes, and they are classified by CVEs, which are types of vulnerabilities, and those get assigned a score. So there's good things about this, right? They try to track the exploitability and likelihood of an attack happening on that vulnerability. They try to track the impact. And then there's like a way to a fudge factor kind of thing where you can add in what your environment looks like and how that reflects you. So the good thing is that it's open, it's standardized, that lets us look at all these definitions and it lets us have a common basis for scoring. But it has a couple of analytical problems with it I want to talk about, and then I'll show you the data problems with it. So this is a quote from the creation of the thing, and this is illustrative of less data, I guess. What I did here to find this is I went through the backlog of back and forth emails between the creators of the standard for like 3 years, just looking at why and how they did it. And what you find there is that they get a bunch of data, they get a distribution back, and then they're like, well, distribution doesn't look normal enough. Let's add some coefficients to it to make it look better. Now, if you base your security decisions based on something that was shifted to the left or to the right a little bit, you can get breached because that was shifted to the left and you made a cutoff decision based on what the score would assign itself. So an 8.5 is no longer as important, but the reason it's not important is because the distribution didn't look pretty enough. The second fail is that people assume that these scores or the disclosure rate of these vulnerabilities is for some reason a process kind of like something in physics or mathematics. So in physics, we have data about spin of electrons, or we have data about the weight of something. Data about processes is entirely different. When they collect these vulnerabilities, there's like 10 people that work there that will get a bunch of emails, and they're a business. They might get, they need to prioritize what they're going to respond to. They need to prioritize which ones are important. Of course, they'll look at Microsoft and Apple vulnerabilities first, and that's the correct thing to do. But in doing so, if you say, since 2006, vulnerabilities have declined by 26%, they haven't. The rate of disclosure may have declined by 26%, maybe because somebody got laid off at the company that publishes them. In fact, I did a blog post a year ago. I don't know why I said a couple of years ago, where I looked at the slope of the rate of disclosure for these vulnerabilities, and I found that there's 3 distinct jumps in the curve. And then I just wrote them an email about it, asking why does this data change rate so much in only 3 places. And they were like, oh, we implemented a new process here, we fired the interns here, and we hired 10 more people here. And not knowing that about your data set and not questioning things like that about your data set will lead to a model that can be as good as you want, but it won't be reflective of the state of whatever you're trying to predict. The third, I put a GIF in here. I don't know how GIFs work. There we go. So the third problem with the score is that the model is a priori. It says, vulnerability got released. Here is the likelihood that it'll get exploited. Here's the impact that it will have. But in the meantime, might have been 6 months ago, a lot of really smart hackers are trying to come up with new ways to exploit the vulnerability. They're coming up with ways that they can squeeze more out of it. They're maybe coming up with new exploit kits and modules that make it easy to weaponize that vulnerability. And so getting a snapshot point-in-time view of it doesn't actually reflect what attackers do in real life. It only reflects what an analyst at a point in time thinks about it. So here's some data about that, and this is an example. This isn't big data at all. Everybody knows about the Heartbleed vulnerability. It affected between 30 and 70% of the internet. It allowed for information disclosure of all types, but the CVSS score is a 5.0. And right away, everybody was like, no, that's crazy, right? There's something wrong with the scoring algorithm. So even the government standards, they published something that was like, take into account the nature of the data being protected. But in reality, it's not the nature of the data being protected that's the problem. It's that the vulnerability is a target of opportunity because it affects a lot of people. It's being actively and successfully exploited on the internet. And frankly, it's easy to exploit. So those things not being captured by the model is how I started to think about the process. And then I did some cluster analysis on those things. So what things are easy to exploit, what things are accessible by attackers, what things have a score in that model that would get ignored by most vulnerability practices. And I found some other ones that are also currently being exploited and probably ignored. And so that didn't really require any data mining. It required an analysis of what it means to be a vulnerability and what it means to score a vulnerability. So this is a velocity of breaches graph for those 5 vulnerabilities. And here's the interesting fact that while Heartbleed made everybody's, it made Wired and Forbes and people started caring about security all of a sudden, in reality, there's not that many breaches happening because of Heartbleed as opposed to other vulnerabilities that are unnamed and unseen. And so this is also the effect of hype or blind trust of some kind of model or somebody else's research. Of course, you shouldn't blindly trust my research either. This data comes from the 30,000, from I think 50,000 businesses. It's an open threat exchange collection, and if one of them gets breached on a particular vulnerability, that gets reported back up to me. After the talk, we can, if you want to ask questions of what a breach means or how that data gets collected, we can also talk about that. So here's where it gets real. We know a bunch of analytical problems with a scoring system, right, or a dogmatic way of doing remediation. And what we want to do is we want to test how good that score is at stopping breaches. That's the goal, right? You want to prevent them. So we need data on breaches. And at Risk.io, we try to aggregate a whole bunch of it from public repositories, from partnerships that we get with places. What I mean by a breach is a vulnerability that is successfully exploited. So maybe nothing happened afterwards, right? Maybe they successfully exploited a computer that hosts Minecraft for someone. But the fact that that exploit happened, the fact that the attack originated and it was successful, is indicative of the base rate probability of that particular type of vulnerability mattering. So we collect a lot of data about that. And then we also have at Risk.io a lot of data about which vulnerabilities exist on systems right now. Our clients upload scans of their environments, and then, of course, we do work on those to tell them what to prioritize. But in the aggregate, we're looking at something like 50 million vulnerabilities from our clients that give us a completely different sample size of those, of what vulnerabilities look like, and then what we're trying to prevent, right? So one could be a training data set, one could be an actual outcome data set, but the two are pretty distinct, right? They come from different businesses. We don't know if there's any actual overlap between them. There's lots of criticism statistically about what I'm about to show you or talk about, but I don't think it really matters because in the end, even if they come from different data sets, those businesses are getting attacked by the same attackers. The logic behind that is often there are targeted attacks, but the ones that make it through and the ones that we can capture are automated attacks that come in massive volumes. We're talking 200,000 attacks per hour or per minute, just people scanning the internet. And at scale, I would tell you that there's no better alternative. You're not going to get a sample set where you have both the live vulnerabilities and the breaches on something that's a representative sample. So let's see what we can do with this. So fudging statistics here using two different samples of, I don't know if it's the same population, but I would say it could be. We got 50 million breaches in the past year. 50 million successfully exploited vulnerabilities. Some of them are as simple as an SMTP mail server. Some of them are root access vulnerabilities. Some of them have probably resulted in financial and data loss. Most of them probably did not. And so what I want to test is I want to test how good CVSS is at catching these breaches. And I'm going to use the live data set of 50 million breaches to do that. So there are a couple ways I could have gone about this. And I think I actually ended up looking at this and doing it. I could have just plugged in every characteristic that I have about a vulnerability. What's the access vector? How old is it? What's the velocity from disclosure to when the patch came out for that vulnerability? Does it have a patch? Does it have an exploit? And just piled all those together and build a regression model to try to predict which ones of those get breached. And it doesn't really tell me much when I do that. Instead, my approach was an epidemiological approach that's much simpler to implement. And as I started with the philosophy, it's a lot more lean to test whether your results actually matter. I did this literally in the console, querying stuff through Ruby or MySQL. So what we want is we want a strategy for catching breaches that is both precise and accurate, meaning that it flags things that end up being breaches in our data set, and that it doesn't flag things that aren't. And so the two things that we care about are predictive value positive, which is how much of the stuff that you flag positive is actually going to get breached on. So let's say I tell you as a security practitioner, here are 100 vulnerabilities, and 40 of them end up being ones that actually matter, that other people have gotten breached on in the past year. So we want a high predictive value positive. We want a high sensitivity. And the reason we want a high sensitivity is because you could have a really high predictive value positive, but to get that, you would have to remediate 2 million vulnerabilities. So it doesn't really mean anything because nobody would be able to get to that. So a sensitivity tells you that how much you're catching of all of the things that people are getting breached on. So this is our baseline. This is what we're working against. If you were just to blindly throw a dart at a type of vulnerability and just guess, the chance that somebody else in the past year had a breach occur on that vulnerability and that you're fixing something that quote-unquote matters in my model would be 2%. And CVSS, the scoring mechanism, does okay. If you only remediate things that have a CVSS score of 10 or above, you're going to catch 3.5% or you will have a 3.5% success rate. And I think CVSS 9 actually doesn't work. I did a round off there. I think CVSS 9 is a little below the random check. So what this shows you is that it's actually a binary variable, right? It's not a score at all, and that's pretty indicative based on our analytical analysis of how the model was constructed and what the data means. So fixing CVSS 10 matters, fixing the rest does not matter. And it is more efficient than working at random. But how can we do better than that? And here, this is what I meant by I could run multiple regressions. I could just throw in every bit of data that we have, but there's a cost to cleaning that data, there's a cost to getting that data, and also there are people who work with me who have security expertise. So I started talking to those people, and I started thinking about some of the work that I've done at Georgia Tech, and I did some work in counterterrorism game theory. So counterterrorism is a field that's a lot like security, but they've been doing it for, 60 years. They've gotten pretty good at it. They prevent a lot of attacks. And they have a methodology towards doing so, where they have feedback loops of data collection. So they collect data about known groups. They collect about how those groups act, what the actual attacks look like, what the quote-unquote breaches look like, and what the past incidents look like. And they come up with ways or strategies for dealing with this incoming data flow through these feedback loops. In security, people don't really do that, and I think it's pretty clear that the model that I showed you doesn't do that. But people also do it in a lot simpler domains. People do it in sports all the time. If the Hawks beat the Bulls by like 2 points, that's not really a win. Most people will go back to the game tape and be like, what could we have done to make that lead differential higher? But in security, if you didn't get breached, most people are like, well, okay, that's great, we won, which is not actually the case. It could have been that you were successfully exploited on something that didn't matter, and then somebody could have hopped away. It could have been that you didn't catch that exploit. So these near misses, and by near misses I mean this data set that I'm describing of successful exploits, is really important in training those probabilities. I'm only saying this to frame how I thought about and how our CEO is a former chief security officer at Orbitz, and how we thought about which factors might we explore in terms of strategy. And so we came up with a couple. There's a repository that's completely open source called ExploitDB, and it just puts proof of concept code, or sometimes working code, of an exploit for a particular vulnerability. There's also another one called Metasploit, which actually allows you to test your environment, so it weaponizes the exploit and allows you to fire it off against any environment to see if you could actually do the intrusion without having to do anything manually. And so our guess was, based on taking a look at types of threat actors and based on taking a look at types of attacks that they perform, that most attacks against businesses are done by people with not a lot of hacking skill. It's not, hyper-specialized PhDs in computer science doing this. It is instead script kiddies is what we call them. So if a business is to be successful, it should be protected against the people that could just point and click at your environment. And what we find by looking at those things is that they're wildly more successful. So if a vulnerability has an exploit module or has a weaponized automated module, so if it has both, if it has the intersection of the two, that's the bottom of that graph there, there's like a 29% chance that you will be catching something that somebody else has been breached on in the past year. Whereas CVSS 10 at its extremes as a strategy can at best do about twice as good at random. So that's not enough to decide which strategy matters, right? And that's just one factor. But if you look at the sensitivity analysis of those, they also catch a significant portion of the intrusions. So by taking a strategy of fixing only the stuff that has weaponized automated code and not looking at any of the other variables that go into a big complex model that gives you a scoring system, you not only are better or more efficient at identifying those breaches and stopping them, but you also have to sift through less stuff. Your security team is more efficient and the strategy is better all around. So I guess the lesson here is that data is everywhere, and more data does not necessarily get you a better answer. It can get you a better fit, it can get you a better model. I saw a keynote recently at a different talk that I think this is a quote from somewhere, but it said, for every really complex problem, there exists a really easy, clear, and incorrect solution. And sometimes that incorrect solution is using too much data. Instead, thinking about something really simple and statistical that you can do on your large data set might be more efficient. And in our case, it was. And in our case, I think, had we gone down the other route, we would have been a lot worse off, we would have spent a lot more money, and we would have gotten to the same result. Thanks. I'm open for questions, and we are hiring people. So take a look at that.
looking at your data, it kind of looks more like it's digitized data as opposed to an analog type of data. But it seems that in your describing how what you see is not really what's most valuable to you, that perhaps the problem is more like an analog, a problem of degrees of something rather than either you caught it or you didn't, because of the things that perhaps you didn't know you didn't catch, or because of things that you caught that were not really that important to catch. Am I capturing the gist of what you said, or am I wrong?
So, correct me if I'm not actually answering your question, and stop me right away. What I mean in terms of prioritization strategy or vulnerabilities in general is that the core question in security is to figure out, if I have a particular type of vulnerability on a particular asset, what's the probability or what's the risk that that poses to my organization? And the goal here is to train some kind of base rate for what the chances of somebody being breached on that type of vulnerability is, so they can use it to guide decision making. And so we could try to assign one to all of the 100,000 types of vulnerabilities that exist out there, but that doesn't really make sense. Instead, we look at which facet or which combination of facets of this data set are important or matter in guiding decision strategy.
Predictive value and sensitivity.
Right.
So your predictive value and sensitivity strike me as kind of an analogy, maybe the radio used a long time ago when it had compression, that kind of thing, where it takes the bandwidth, it scrunches it down, and then takes certain sets and highlights certain bandwidths to make sure that they don't fall outside of the range of acceptable RF the frequencies for the speaker systems that they're wanting to be played on, that kind of thing. So you're talking in terms of vulnerabilities that you can catch, vulnerabilities that are important, remote versus maybe internal type vulnerabilities. That goes into this ranking?
Yeah. So in these rankings, right, the only things that go in, so into the CVSS score, you mean? Yeah, so that model that the government releases looks at all of those things. Not all of them. It looks at the access vector, the complexity of access, the integrity of access. It looks like at the impact, at the exploitation. I guess the point earlier was that those things being done by analysts and then taken as data is not actually reflective of the state of affairs in the world, and the state of affairs being what attackers do and how attackers get into businesses.
Thank you for that. Any other questions? Chances are you may never have this chance again.
I expect a lot of you to, frankly, disagree with my operational approach to data science, right? This is like a scrappy startup approach that makes sense for us, but at a bigger organization, I'd love to hear your feedback on where this just wouldn't work for you guys.
Are there
I was just going to ask, other than Metasploit, are there any other weaponized tools that you benchmark your data against?
No, but there is a really good paper out by two Italian guys in the University of Toronto. It's Luca Alati is the first author in the paper, and they look at black hat exploit kits. So they'll go on like those forums and they'll find all the stuff that you could potentially buy weaponized, and that's not public data. They don't release it to the public. I'm really interested in working with them. I've been talking to them about analyzing against something like that. But you're right? These are just the really simple, publicly available indicators that would lead to an attack, and I've proven with a big data set that that is correct. There are probably things that, more precise analysis or more precise analysis of those exploits would also get us.
Thank you.
My question is in regards to, taking combining all these threats and kind of applying heuristics to it. Is that something that you're, going to develop in the future?
What do you mean by threats?
So right now you're taking known exploits and you're categorizing them and scoring them. But let's say you've got new threats that are coming about. Could you, use this massive amount of data from your your perspective from all the companies that are on the SaaS service that I guess kind of heuristically determine, okay, these are some new threats being targeted to certain
Okay.
companies, so to speak.
Yeah, so you're talking about the difference between this being prescriptive and predictive, right?
Correct.
So, yes, that's something we're going to work on. I think that might lead itself better to a non-heuristical approach, right? Because checking those models against something is very difficult. But also, the way that you would check that your prediction was correct, you need two things to happen. You need, when the vulnerability comes out, for somebody to weaponize it or for somebody to figure out a way to exploit it, right? So that's one event that you would be trying to predict. And then the other event that you would be trying to predict is that somebody can catch that that breach occurred. So you will get the data about the breach occurring, right? That's how you would confirm if your model is correct. And I think the issue with doing that is that by the time that comes out, so much time has passed that the value of that prediction might be gone. So I think a cooler thing, or not a cooler thing, I think a really similar thing, but it reframes the problem, would be to figure out how much time passes between, so like I know which things matter because I have a massive data set. How much time passes between when they're released or when we first hear about them and when they start mattering? And then can I predict that time frame? So that's, I guess it's a different question, right? It's like, will this matter later? Because I think confirming a model about actual attacks and exploits, breaches happening on a particular type of CV is very difficult. So in fact, what we see mostly is that the most successful attackers are using things from like 2002 and 2003 on archaic systems that just haven't been updated. So, I mean, there's tons of activity on new things as well, you know, like Elasticsearch vulnerabilities or Ruby on Rails vulnerabilities. But the massive slew of breaches happens on like Windows NT vulnerability. Somebody runs this thing somewhere and forgot about it.
So that's the 30% you talked about, slider and 30 or 40%.
Yeah, that's why we catch so many of them, right? Because we already know everything about how they would get attacked. And then if you filter on that facet, chances are that somebody's attacking them if you have all that data about them.
I have a question. So you talk about kind of the predictive capability to identify vulnerabilities. Do you think that has applications in incident response as well, in addition to vulnerability detection and demonstrating kind of these massive exploitations?
So you're asking a question about the last answer, right? So I think some people actually do this work in incident response. We don't actually see any data from incident response. I mean, we do in that our data is generated by people responding to incidents, but the steps that happen in between, or like how somebody found this thing, we don't really know. There's a couple ways they do it, right? They do some forensic analysis, whatever. And I think the ways in which they do that to find the particular type of vulnerability that we see being breached, that's the kind of data that you would need to make that prediction accurate.
But the reason I ask, there are some folks that have this so-called automated incident response. I'm assuming they're using some sort of predictive model as well to kind of, take a snapshot of their network and try to identify where is the most likely place for someone to try to enter.
Yeah, so there's a couple of other companies that take a different approach to it. I think you're talking about like Red Seal Networks or something like that. They look at topology as their risk model. So our risk model is threat activity. Their risk model is topology. I see value in both for sure. So there's a really specific reason when we start, because we started with just a big data set, and then we were like, how do we make something that actually is useful? The reason we didn't go the topology route is not because we couldn't collect data about it. There's a lot of academic literature in game theory about how if the cost to the attacker is really low, so if trying to attack again is really cheap and if being detected is really hard, which is cybersecurity by the book. It also happens in San Francisco bicycle thieves and counterterrorism. So the literature says that the network topology doesn't end up mattering because jumping from asset to asset is infinitely cheap. So there's some threshold at which it doesn't matter what your topology is, and my really bold guess is that cybersecurity is one of those domains, because what does it cost to run network time and run through Tor?
I think that's kind of the thesis for the folks like at Shape Security, where they're making it more expensive to leverage botnets to make those attacks by obfuscating the data kind of dynamically.
Yeah. that makes sense. So that's like an outside layer of protection, right? They also say, like, who cares about what happens internally? You're going to get hacked if you're going to get hacked externally.
Any more questions?
I don't disagree with your philosophy on data science, and that was refreshing to see. So I guess my question is do you have any examples of, on one hand, you talk about being doing things simpler and using domain knowledge, and on the other hand, not to chase the latest tool or the latest algorithm. But I think you talked a little bit about how you started simple and then you had to go away from some tools like MongoDB. Can you give an example of when you knew it was right to go from the simpler model or some of the tools that you're using and start to adopt something new, not because it was the new shiny object, but because you had to?
That's a really good question. So I think that question this is not my domain expertise, but I just listened to our chat between all of our developers. Just to clarify, you mean both in terms of technology and in terms of model complexity, right?
Right.
So I think that question is easier answered in terms of technologies. And that's a question of, for us, it has been, gathering analytics about how your application is performing and how your users are responding to that performance. So for us, we were running this MongoDB and Solr setup for a long time, and it was working just fine to do the predictions. It took a while. We could keep improving it and making it a little faster until we got enough clients where our data set got to be 50 million vulnerabilities instead of 5 million vulnerabilities, and that things would take just days or many, many hours, and clients couldn't use the tool, right? Somebody would sign up for the tool, and it would take 3 hours for stuff to load before they could even use it, and they'd be like, why did I sign up for this? So once you see things affecting the business, right, or once you have data showing that customers are pissed off, that's a really good time to reevaluate. So we scrapped those two and we moved to Elasticsearch, which is recently what Wikipedia switched to as well, and it has been like a godsend. We bubble up the stuff that we care about in MySQL to Elasticsearch, and we can query in our biggest clients. I'm trying to think. Call it 5 million vulnerabilities can get queried in about 10 seconds. And those are full documents. But in terms of like what that inflection point is, it's customer driven. In terms of models, I'm afraid to answer the question because that's like my decision, right? I made it myself. I can't describe the process from the outside. Part of it is laziness, of course, because why not try the easier approach first? Part of it is that in a business sense, so I ran the multiple regressions on all the facets of a vulnerability. In a business sense, it's really hard to justify why that particular coefficient leads you to make a prescription for your customers. And so once you realize that I can't give a talk about it and have people who don't know security understand what I'm talking about, that's when you probably should stop. There are other scenarios where people love a complex algorithm, right? Like pull something out of Python scikit. I'm not going to tell you what the clustering algorithm does, right? But people would just blindly trust it. I just think it depends on the domain. In cybersecurity, we're making prescriptions about what to fix, and we claim that it'll have some benefit. It's a preventative science. So there, people just want something they understand, rather than, we clustered on a lot of things. That said, I think there are types of customers that would also be okay with that kind of algorithm, right? There's security customers that do machine learning on IP reputation data, and that stuff works really well, and it has scientific proof behind it. It just depends on what your target market is and what confidence you have in that model being correct domain knowledge-wise rather than correct fit-wise. I would say that's the best way I could tell. Because I have many models where I could tell you that fit-wise this is awesome, but like, does it actually describe the state of affairs in cybersecurity? I don't know. This does, for sure.
I have a question about sort of the time ordering of the sequence that you're looking at. If I understand correctly, you're trying to prioritize the vulnerabilities in some order so that people know which ones are most important to fix. And your priority is based on their appearance as weaponized code. But doesn't their appearance as weaponized code already indicate that they're being used as vulnerabilities somewhere, and that wouldn't simply seeing what's actually being used as an attack, as an exploit, simply give you a 100% success rate for predicting what vulnerabilities are important to fix?
Right. So, yeah, your question is dead on. I'm not describing the process by which we prioritize vulnerabilities. I'm describing how I learned an insight about which facet is predictive of this thing. So, a vulnerability might have an option for weaponized code. Is it being used or not is a different question. So what I showed here with this data is that having a weaponized exploit and metasploit, or just having an exploit, is indicative that the vulnerability is being actually attacked. Your second statement that if it's actually being attacked, it matters. I agree with it. Our actual prioritization models do that too. The issue is that the data set of what is actually being breached is just the tip of the iceberg. So I'm looking for other indicators of what's below the surface that my incoming breach data doesn't tell me. So that's why, in reality, that model uses 16 factors. But those factors are not identified that way. They're identified through thinking about what the security thing is and seeing what the security implications of it are, and I guess what it means in terms of probability of breach. Cool. Thank you, guys.